Okay, so hello and welcome back. So the next question that we have here is basically question number 17, and you want to find the relationship, a relationship or the relationship, depending on the situation, between A and B, such that f defined by this function is continuous at x is equal to 3, right? So basically it's a simple question. And first I was writing this down and I got a little bit confused, but basically it's a simple question. So basically the only thing that you need to do here for this function to be continuous at x is equal to 3 or continuous at any other point for that matter is that you need to make sure that basically the conditions that we know for the continuity of a function at any point is fulfilled, or the conditions are fulfilled. So you know that basically the condition for any function to be continuous at any point is that basically the limit of the function at that point exists, the function is defined at that point, and then these two values are the same. If that's the case, then that means that the function is continuous at that point. Otherwise it's not, right? So then I can say that basically in order for f to be continuous at x is equal to 3, the following conditions have to be fulfilled. Number one, f of x at x is equal to 3 has to be defined. That is, f of 3 has to be defined, right? And number two, basically the limit of f of x as x tends to 3 has to be defined, and then f of 3 is equal to, so the value of the function at x is equal to 3 has to be equal to the limit of the function as x tends to 3, meaning that this condition has to be true. So now we can take care of them one by one. So what I need to do, so first of all, the first case, f of x at x is equal to 3 has to be defined, meaning that f of 3 has to be defined. This is already defined by the function, meaning that f of 3, as you can see here, x less than or equal to 3. So f of 3 would be basically calculated using this. Substitute x by 3, you'll get 3a plus 1, right? So f of 3 would be 3a plus 1. Number two, the limit of f of x as x tends to 3 has to be defined, meaning that basically for this limit to be defined, then you know that the left hand limit and the right hand limit have to be equal, meaning that the right hand limit and the left hand limit being equal means that the limit of f of x as x tends to 3 from the right, you have to essentially look for values of x greater than 3. Values greater than 3, you will end up with bx plus 3. So the limit of bx plus 3 as x tends to 3 has to be equal to the limit of the function as x tends to 3 from the left, which means that you have to look for values less than 3. And that would be this part over here, ax plus 1. So the limit of ax plus 1 as x tends to 3, and since these two are polynomials, you can simply substitute x with 3, meaning that 3b plus 3 is equal to 3a plus 1, which gives you this condition over here. And that basically means that 3b, so this is basically the condition for the limit to be defined. Now we said that basically the value of the function at x is equal to 3 has to be equal to the limit. So that means that I should write, so this is the condition for the limit, meaning that these two have to be equal. 3b plus 3 has to be equal to 3a plus 1, and that has to be equal to basically the value of the function at x is equal to 3, which is 3a plus 1. So 3a plus 1, this has to be true. right? Which ultimately means that since these two are the same, that means that 3b plus 3, which is equal to 3a plus 1, has to be true. Meaning that 3b, and subtract a 1 from both sides, you'll get 3b plus 2 is equal to 3a. And therefore this is the condition for, this is basically the condition for f to be basically continuous at x is equal to 3. Or you can say a relationship between a and b, such that when the condition is fulfilled, then basically f is continuous at x is equal to 3, right? So that is basically question number 17. We have another question over here, and that is basically question number 18, exercise number 18, and that is for what value of lambda, is the function defined by is f continuous at x is equal to 3, as x is equal to 0, I'm sorry. What about 1? What about x is equal to 1? And the function that we have is f of x is equal to lambda times x squared minus 2x for x is less than or equal to 0, and 4x plus 1 for x is greater than 0. Okay, so this is again the same question. So what I need to do is that I can calculate the value of f of x at, for example, at x is equal to 0, right? At x is equal to 0, what we have is basically at x is equal to 0, basically f of x is equal to lambda times x squared minus 2x. F of x is equal to lambda times x squared minus 2x. And the limit of the function is equal to the limit of f of x as x tends to 0 from the right, for example, going for values greater than 0, that would be the limit of 4x plus 1 for x when x tends to 0, which is equal to 1. 4 times 0 is equal to 0, plus 1 is equal to 1. And the limit of f of x as x tends to 0 from the left is equal to the limit of values less than 0 is basically the limit of lambda times x squared minus 2x as x tends to 0. And if I put x is equal to 0 here, this is 0 minus 0, 0 times 0 is equal to 0, so the limit of 0 would be equal to 0. And which is of course not possible, right? I think it's not just at x is equal to 1. At x is equal to 1, it's just not possible because the limit of because the limit of f of x as x tends to 0 does not exist. It cannot exist because the limit of f of x at x is equal to, when x tends to 0 from the right, you have the limit of 4x plus 1 when x tends to 0, that's equal to 1. The limit of lambda times x squared minus 2x is equal to 0 squared minus 0, which is equal to 0. 0 times lambda is equal to 0. And so 0 cannot be equal to 1. Therefore, the limit of f of x when x tends to 0 does not exist, and therefore f is not continuous at basically at x is equal to 0 for any value of lambda, at least for real values. I can see in the solution over here that they've said that for no real values of lambda, but we are not working in the set of imaginary numbers, so that's not really important right now. But as far as we are concerned, as at least as long as we are working in the set of real numbers, for any value of lambda, f cannot be continuous at x is equal to 0. At x is equal to 1 here, we have at x is equal to 1, we have basically the value of the function at x is equal to 1 is equal to, you have to use this part of the function because 1 is greater than 0, of course, right? So 4x plus 1. So f of 1 would be equal to 4 times 1 plus 1, which is equal to 4 plus 1 is equal to 5. And the limit of f of x as x tends to 1 from the right, and you can see that basically over here, the limit of f of x as x tends to 1 from the right or left, you can use this part over here, because basically f of x is not broken at x is equal to 1. So I can just simply write the limit of f of x as x tends to 1 is the limit of this part over here, 4x plus 1. So I can write basically the limit of f of x as x tends to 1, not from the right or left, but just simply from just tending to 1 is equal to the limit of 4x plus 1 as x tends to 1, and that is equal to 4 times 1 is equal to 4 plus 1 is equal to 5. And therefore you can say that for any value of lambda, for any, basically at least for, therefore you can say that for any real value of lambda, f is continuous at x is equal to 1. You can see that, and we are saying this because you end up with no condition here. If there was a condition, then we would say that, for example, for such and such values, for example, f of x is continuous at x is equal to 1. Otherwise, you can see that the value of the function is already equal to the limit of the function at that point, which means that basically the lambda is just not important. It can take any value and the function would be continuous at x is equal to 1. Right? So that's one thing here. So this was question number 18. Now question number 19 is as follows. Okay, so the next question that we have is question number 19. where we want to show that the function defined by, we want to show that the function defined by g of x, which is equal to x minus the basically the greatest integer function, which is basically, this is the notation for it, is discontinuous for at all integral points here, and of course basically this notation denotes the greatest integer, denotes the greatest integer less than or equal to x. Less than or equal to x. So if basically, if your function is the greatest integer function is basically, so first you need to know what is the outputs of the, to draw the graph of this function. Of course, it's not really necessary to draw the graph of the function, but just for the sake of, as a reminder, you can of course draw the graph of the function in the following way. So basically the greatest integer function is, so basically basically you can write that f of x is equal to this notation, which denotes the greatest integer less than or equal to x. Meaning that, for example, if suppose that, for example, your input is equal to 0, then basically, of course, since 0 is an integer itself, then the value of the function becomes 0, right? Suppose that the input is, and this is, for example, suppose that this is 1, 2, 3, 4, and so on and so forth. This is -1, -2, -3, and so on and so forth. Now, suppose that, for example, your input is some value between 0 and 1. The greatest integer less than or equal to 0.5 is 0, and therefore your input stays still at 0. And basically, and you can just keep going using the same logic. You can show that basically the value of the function remains at 0, and so on and so forth, all the way up to 1. Meaning that when you get to 1, the greatest integer less than or equal to 1 is equal to 1. That means that the value of the function then basically jumps up over here. And then you can just keep going in the same way until at this point the value of the function jumps up to 2. And then at this point the value of the function jumps up to, at this point the value of the function jumps up to 3, and so on and so forth. That means that at these points you have basically hollow circles. At this point you have a hollow circle, at this point you have a hollow circle, at this point you have a hollow circle, and these are all filled circles. And so you can basically draw the graph of the function that way. And you can just keep going, meaning that, for example, at x is equal, at y is equal to -1, -2, -3, then your outputs become these outputs. And again, you can have these outputs over here, and you can have these outputs over here. And that's basically the greatest integer function. right? So to sum it up, this is f of x is equal to the greatest integer function denoted by this. Now, if you have basically the function basically denoted by, and when we say basically at all integral values, that means that at all of the, that's in simple language, that means it's at all of the integers, meaning that at 0, 1, 2, 3, 4, and -1, -2, -3, and so on and so forth. And the function denoted by g of x is equal to x minus basically the greatest integer function, then naturally that would be some function like this, meaning that, for example, at x is equal to 0. Okay, so I did basically try to graph this function in many different ways. I tried to use Desmos.com, some other graphing calculators, and I did try to graph the function manually. It's not easy to graph this function, okay? It turns out that the function is actually so the function is basically something like this, meaning that basically, for example, at x is equal to 0, the output of g of 0 becomes 0 minus 0 minus 0, which is equal to 0. At x is equal to, for example, 0.5, the output of the function becomes 0.5, and so on and so forth until you get to 1. When you get to 1, the output of the function all of a sudden, so that would be, so at x is equal to 1, the output of this function is equal to 1. So 1 minus 1. At x is equal to 1, the output of this function is 1. So 1 minus 1 is equal to 0. So it seems that I have made a mistake here. G of 1 would be basically g of 1 is 1, so 1 minus 1 here is equal to 0. And so the function is at this point. And I suppose then you would have the same thing repeated indefinitely in both directions, meaning that suppose that, for example, x is equal to then, for example, 1.5, right? If x is equal to 1.5, what happens is actually an interesting function. So when x is equal to 1.5, for example, then basically so or even 1.2, for example. Suppose that x is equal to 1.2. Then basically for 1.2, g of 1.2 would be equal to 1.2 minus, at 1.2 the output of this function is still equal to 1. So you'll end up with the 0.2. So that means that again the function is at 1.2, it's going to give you the same output until you get to meaning that that's at 1.5, the output of the function is again at 0.5, and until you get to 2, right? Until you get to 3. 0, 1, 2, until you get to 2. So at x is equal to 2, basically g of 2 would be equal to basically 2 minus, and the output at 2 is equal to 1, so the output becomes 1. The output becomes, no, again I made a mistake here. So at x is equal to 2, what happens is that you have 2 minus, and the output of this function at x is equal to 2 is equal to 3. Is equal to 2, is equal to 2. So 1 minus 2 is equal to 0, 1, 2. At x is equal to 1, 2, the output of the function is at 2. So 1 minus 2 is equal to negative 1. This function is creating trouble for me. So let's first take care of the output as at 1, and then we will take care of the other outputs. So at x is equal to 1, then g of 1 is equal to basically 1 minus the greatest integer function applied to 1. Applied to 1, the output is 1. So 1 minus 1 is equal to 0. So the output jumps to 0, which means that basically this is correct. And then as I move towards these positive x's, the output basically keeps rising and rising in the same manner until I get to 0, 1, 2. So when x is equal to 2, then g of 2 is equal to 2 minus the greatest integer function applied to 2. So that is equal to 2. 2 minus 2 is equal to 0. Again, basically, the output jumps to 0. And the same thing keeps happening over and over again until you get to infinity. And I suppose the same thing happens here as well. So you have basically this function over here. So this is basically your function, and that is basically the function g. Now, what you want to show is that basically you want to show that this function is discontinuous at all integral points. At all integral points, right? Now the logic that they have used over here in order to show that this function is discontinuous at all integral points is that basically is as follows. It's a little bit unusual logic. So the logic that they have used is that basically let k be any integer. Let k be any integer, right? Now the left hand limit of the function f of x as x tends to k, the LHL of basically the function is equal to the left hand limit of the function is equal to the limit of f of x as x tends to k from the left. It's actually interesting logic that they have used, but mathematically it has problems, meaning that of course you have to I mean normally you have to prove this. You cannot just write that well, of course, I would accept that as I mean, one would accept that, one could also accept that as correct mathematics. There is no problem with that. So the logic that they have used is that basically since you want to show that basically this function is discontinuous at all integral points, you can assume that k is any integer. K is any of these integers, and you can see that the function is behaving in the exact same way at all of these integers. At any integer, the function is rising, getting to the next integer, and basically when it gets to the next integer, the value of the function has already become has already gotten very, very close to 1, and then again the function jumps back to 0, again the function gets very close to 1, and so on and so forth, all the way from negative infinity to positive infinity. So now in order to evaluate this limit, what you can do is that what this limit means is that it's saying that the limit of f of x, the limit of this function, as x tends to k, and k is any integer, and x is tending to k from the left, meaning that for example, suppose that x is tending to, for example, 0 from the left, and so you can see that basically the value of the function as x tends to 0 is very, 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 meaning that if I get closer and closer to 0, the values of the function are getting closer and closer to 1. So then you can say that basically, and the same thing happens if you approach any other integer for that matter, meaning that, for example, suppose that I approach, for example, 1 from the left. As you can see, as I get closer and closer to 1 from the left, the value of the function is getting closer and closer to 1, which means that the limit of f of x as x tends to k from the left, meaning that as you approach any integer from the left, is actually equal to 1, right? Now, on the other hand, you can show that basically the right-hand limit, the RHL, the right-hand limit is equal to the limit of f of x as x tends to k from the right. And you can approach a couple of these integers in that manner, meaning that, for example, you can approach 0 from the right. You can see that as you approach 0 from the right, the values of the function are getting closer and closer to 0. And the same thing happens over here, the same thing happens over here, and the same thing happens all throughout the domain of the function. And therefore, this limit is equal to 0. Now, so of course you can argue that here at x is equal to k, and k is basically here any integer, your RHL is not equal to the LHL, and hence the function is discontinuous at discontinuous at all integers. Actually, very interesting logic. I like the logic that they have used in order to solve this problem, because otherwise, for example, if I were to solve this problem, I would probably that's the only way that you can solve this problem. Otherwise, then you would get into trouble. Okay, so that was question number 19. Now, question number 20 we have is the function defined by f of x is equal to x squared minus sine x plus 5 continuous at x is equal to pi. So you have the function basically f of x is equal to basically x squared minus sine x plus 5, and you want to know if this function is continuous at x is equal to pi. So you can just simply see if the function is continuous over there. So you can find the limit of this function at x is equal to pi and the value of the function at x is equal to pi, and see what you will have. So the limit of this function as the limit of f of x as x tends to pi is equal to is equal to, well, the limit of basically x squared minus sine x plus 5 as x tends to pi, and that is equal to basically pi squared. That is equal to pi squared minus sine pi plus 5, which is equal to pi squared. Sine pi is equal to 0, right? Sine of 180 degrees is equal to 0, minus 0 plus 5, which is equal to pi squared plus 5. Now the value of this, and of course the value of the function is the same because it's a polynomial. You know that basically f of pi is equal to, well, pi squared minus sine pi plus 5, which is equal to pi squared. Sine pi is equal to minus 0 plus 5, which is equal to pi squared plus 5. And as you can see, basically the limit of f of x as x tends to pi is equal to f of pi, and therefore you can say that f is continuous at x is equal to pi. So that is question number 20. Let me take it. Okay. So question number 21. Question number 21, we have question number 21, we have discussed the continuity of the following functions. Number 21, part A, we want to discuss the continuity of, for example, f of x is equal to sine x plus cos x. So let's see if this function is continuous. Okay, so here basically we have, this question has a couple of parts, meaning that it has part A, which is f of x is equal to sine x plus cos x. Part B is basically you want to show that this function is continuous, which is basically f of x is equal to sine x minus cos x. And C is basically f of x is equal to sine x times cos x. Now here, of course, most probably you can actually use, well, let's not discuss that because I'm not really sure about it. But over here, what you can do is that you can use the theorem that we had before about the continuity of these functions. So basically we had two theorems here. One of them is about composite, functions or composition of two functions. And theorem number 1 was about basically the sum and difference and product and the quotient of two functions. So basically what we discussed before was that suppose that, for example, f and g are two real functions. Suppose that f and g are two real functions, and functions which are basically continuous at some real number c, right? Then if that is the case, then number 1, you can say that f plus g is continuous at f plus g is also continuous at x is equal to c, and number 2, f minus g is also continuous at x is equal to c, and number 3, f times g is also continuous at x is equal to c, and number 4, f divided by g is also continuous at x is equal to c, of course, provided that f by f that basically g of c is not equal to 0, right? So this was the theorem that we had. So now what we can do is that we can actually use this theorem in order to show that these three functions are continuous. And the way that you can use them is that, first of all, you have to show that, and basically sine x is a continuous function and cos x is a continuous function for all real numbers, and then based on that and based on this theorem, then you can conclude that basically the three of these functions are continuous functions, because this function is nothing but nothing but the sum of the two functions. This is the second function subtracted from the first function, and this is the product of the two functions. And of course here basically for sine x by cos x, which is tan x, is not continuous at some points, because for example at pi by 2 it's not continuous, because then at pi by 2 the function is actually, the function is not defined, but then cos of pi by 2 is actually, so you'll get into trouble over there. But these three would be continuous, of course. So now let's basically do basically these three. So first we need to show that sine x and cos x are continuous functions. Now, okay, so now there is actually an interesting way of showing that the sine function is a continuous function. Of course, you know that the condition for any function to be a continuous function. And so basically if I say that, for example, let g of x be equal to sine x, meaning that sine x is some function g of x, for example. I'm just considering that the sine function. And let k be any real number, and of course you know that the sine function is defined for all real numbers. So if I imagine that k is any real number, then I need to show that basically the sine function, I need to show that basically that the limit of the sine function at any k is defined, and at any k the value of the sine function is equal to the limit of the sine function as x tends to that point, meaning that for example, suppose that this is the sine function, and I need to show that basically, for example, at this point, for example, x1, the value of the sine function is this value over here, is this value y1. And then I need to show that basically the limit of the sine function, meaning that the limit of sine x as x tends to x1, is equal to basically sine of x1. So I need to basically show this. So first we need to show that the limit of the sine function at any point is is defined, right? And for the limit to be defined, basically you have to take the left hand limit and the right hand limit and show that those two limits are equal to one another. So in order to do that, basically what you can do, if k is any real number, then you can say that basically and pay attention to the logic that is used here in order to find the limit of the sine function. Is actually interesting. So the left hand limit of this function, which we can call LHL, the left hand limit, is equal to the limit of basically the limit of sine x, as x tends to k, from the left, right? Now what this means is that basically you have in order to evaluate this limit, you have to understand a few simple things. Now suppose that, for example, this is the sine function and this is, for example, pi by 2, right? If this is pi by 2, now you can imagine that here, that in this situation, basically your k is pi by 2, for example, and x is tending to pi by 2. So what happens here is that as x tends to pi by 2 from the left in this manner, so ultimately x gets very close and very close to pi by 2, meaning that there is a thousandth of a unit or 1 millionth of a unit, and so on and so forth, difference between x and pi by 2, but ultimately x is less than pi by 2, right? Which means that the value of x plus and if you basically denote that distance between x and pi by 2 by h, for example, then you can say that x plus h is equal to pi by 2, right? Now in this situation, if I say that basically this pi by 2 basically represents any k in the domain of the sine function, then I can simply say that, of course, at any rate, since x is tending to k from the left, x is always going to be less than k, and this is also always true, meaning that x plus h is always going to be equal to k. And so now there is this relationship between x, h, and k, right? And so what that means is that I can write this limit as, now imagine that, for example, k is some number in the domain of the sine function, x is tending to that k. The difference between x and k is h, and this relationship exists between x, h, and k. So what happens is that then you can write this limit as the limit of basically basically instead of x you can write basically k minus h, right? K minus h. And as x tends to k over here, as you can see, as x tends to pi by 2, ultimately h tends to 0, right? As x tends to k, meaning that as x gets closer and closer to pi by 2, or gets closer and closer to k, whatever the value of k might be, the value of this h gets closer and closer and closer to 0. Then I can write over here h tends to 0, And now this limit, I can actually calculate it, but this limit, there is no way for me to calculate it. And that's the interesting part here. So what that means is that then I can write this as, and you know what is, and of course I have to write this as the sine of k minus h. I have to write this as the sine of k minus h. So that is the limit of this. Now this limit we can simply calculate, meaning that first of all, you know that basically the sine of x minus y is equal to sine x cos y plus or minus cos x sine y, right? And so I can write this as the limit of basically sine of k minus h based on this formula would be basically sine k cos h minus cos k sine h, the limit of this as, excuse me. Okay, so now basically we have the limit of this expression as h tends to 0, right? And then you can simply calculate this, meaning that of course you can separate these, and based on algebra of limits, you can write the limit of basically sine k cos h, and as h tends to 0, minus the limit of cos k sine h as h tends to 0, and then you can write this as basically and then as h tends to 0, this becomes basically sine k cos 0 minus cos k sine 0, and you know that basically sine 0 is equal to 0, so this whole thing goes to 0, and cos 0 is equal to 1, so this becomes basically sine k, which ultimately means that basically the left-hand limit of basically sine x as x tends to k tends to k, the left-hand limit is equal to sine k, right? So basically that means that the limit of sine x as x tends to k from the left, and k being any real number, is equal to sine k, and here basically k belongs to the set of real numbers, right? So that's one thing. And then you can do the same thing for the right hand limit, meaning that you can write the limit of sine x as x tends to k from the right is equal to basically, again, you can imagine that there is some x tending to some k from the right, meaning that again, I have to show you over here, or I have to even show myself, because these things you have to know what you're doing. So this is your k, this pi by 2 represents your k, and your x is tending to k from the right, right? So which means that essentially your x is somewhere over here, and this is your k, and this distance is your h, which means that you can say that basically this k plus this h is equal to your x, right? So k plus h is equal to x. So basically when you want to write this relationship between x and k, so here you can see that I have written x plus h is equal to pi by 2, and that's because basically x is tending to k from the left. So the logical basically conclusion becomes basically this. But when your x is tending to k from the right, then the logical conclusion becomes this, and these things you really don't have to memorize, because it's just not possible to memorize it. In the first, of course, if it was possible, it would be not bad, of course. But it's just not easy to memorize these, because then you will end up with a whole bunch of things that you would have to memorize, and then I'm not even sure how long you would be able to even basically hold on to all of those things in your memory. So it just, I suppose it would never actually work for any serious or real purpose in mathematics, meaning that if you want to actually do something with your mathematics, it has to be something that something practical, and practical means that you can keep it for as long as you live, probably, because you want to work with it, right? So so then basically, long story short, the relationship between x, h, and k is basically this thing over here. And then you can basically write here, basically that you can, instead of basically x, you can write k plus h. So you can write this as the limit of sine k plus h, as, and then as x tends to k from the right, then of course, as you can see, as x is some number over here, and it is tending to your k. That means that the distance between x and k is getting smaller and smaller and smaller. In other words, basically your h, which is the distance, is tending to 0, right? So that means that over here I can write as h tends to 0. Now again, this is the same story, the same formula over here, except that instead of a negative sign, you would get a positive sign, meaning that sine of x plus y is equal to sine x cos y plus cos x sine y, right? So which means that basically this is equal to the limit of sine of sine x cos y, plus cos x sine y, as h tends to 0. And this basically, you can basically separate these two. You can write this as the limit of sine x cos y as h tends to 0, plus the limit of cos x sine y as h tends to 0. And you know that this is the same thing as basically sine as basically you can write this as sine x cos, oh, I made a mistake here, I'm sorry. I did make a mistake here. So instead of basically x and y, you have to write actually k and h. So over here you have basically k plus h. So this is sine k cos h cos k sine h. And over here you have basically the limit of basically sine k cos h cos k sine h, right? and then this is equal to sine k, and then this is, as h tends to 0, this becomes cos of 0 plus, as this is basically cos k sine 0, and you know that sine 0 is equal to 0, so this whole thing becomes 0. Cos 0 is 1, so this is equal to sine, of course this is equal to k, I apologize for this. This is equal to sine k. So basically, long story short, you can say that the limit of sine x as x tends to k from the right, meaning that if you have the function sine x, and then x tends to any k in the domain of the sine function, meaning that suppose that you have the sine function over here, and the domain of the sine function is negative infinity all the way up to positive infinity, right? And there is some any k belonging to the set of real numbers in the domain of this function, and now x basically tends to any of these k's from the right, right? So when that happens, the limit of that function, the limit of that limit would be equal to sine k, right? So which means that then you can write the limit of sine x as x tends to k from the right is equal to sine k, and this k belongs to the set of real numbers. And so, long story short again, so what this over here, we said that the limit of sine x as x tends to k from the left is equal to sine k. The limit of sine x as x tends to k from the right is equal to sine k. So these two limits are both equal to sine k. And therefore you can say that basically the limit of sine x as x tends to k is equal to sine k. K belonging to the set of real numbers. K belonging to the set of real numbers. So this basically shows the limit of the function sine x as x tends to k. In the next video we will continue with this idea, and then we will show that basically the function sine x is a continuous function, and we'll have to do the same thing with the cos function, and then put the whole thing together and show that those three functions are continuous functions. I'll see you in the next video, and thank you.